Good day guys, welcome back to another tutorial on STS 201. Sorry I've not been posting videos for some time now. I was actually indisposed, and though I've been feeling alright for quite some days now, but I was told to have enough rest, not to engage in any strenuous activities, so I had to pen so many things in order to have enough rest. Sorry for that guys. So we are back, and hopefully I'll be posting more and more videos now. Today we're going to be treating ANOVA, and ANOVA means analysis of variance. In this, I would advise you guys to go ahead and know the terminologies, because there are so many terminologies in this note. Please try and know them, understand what each of them, because I cannot take everything here. I'm going to focus on the calculation here, the calculation aspect. So the terminologies, please try and know them, because sometimes you get questions on meaning of all those terms, replications, treatment, and the likes. You get questions on them. Okay, so today we're going to be treating ANOVA, and we're going to be treating one-way ANOVA. We have one-way ANOVA and we have two-way ANOVA. Going straight into what we have today, I'm going to write out a question. So from the question, I will explain the terms that I can explain. I'll explain them, and we'll move on from there. Okay, quick writing out the question. Now, this is the question we have for today. We're treating the one-way ANOVA. Now, one-way ANOVA is a test of hypothesis. ANOVA itself is a test of hypothesis. I wonder why they didn't teach you test of hypothesis before taking ANOVA. Some other tests of hypothesis like the t-test, student t-test, z-test, and the likes. I wonder why they didn't. But then, let's just go on. So it's a test of hypothesis, and here let me give a practical example. Let's take, for example, this A, B, and C. They are called treatments. They are called treatments. And let's take, for example, now, let's assume some plants were subjected to this. Let's assume we planted some things, and maybe these are the number you planted. You took a particular plant, you planted it, and in the space of 1 week, you tried and probably you tried to get the number of leaves the plant produced in the space of, from the time you planted it to probably after like some days, let's say a week. You try to know the number of leaves the plant produced based on different treatments. So this might be treatment A. Maybe treatment A might be, probably you subjected the same kind of plant, you subjected them to a level of water, maybe 10 mils per day, and probably treatment B, you subjected them to 20 mils per day, and treatment C, you subjected to maybe 30 mils per day. Now, trying to understand if there is a difference between the treatment, that's when you are talking of analysis of variance. Trying to see if there is any difference in the level of treatments that each of these groups of plants were subjected to, then that's when you're talking of carrying out analysis of variance. Okay, so treatment A, now the ones at the side there, they are called replications. These ones are called the treatments, these ones are called the replications. So this is one plant, this is another plant, this is one plant, another plant, another plant, another plant. You replicated like one plant 1 subjected to this treatment A, another plant 2 subjected to treatment A, another plant 3 subjected to treatment A, like that. Now this is in a group. Now this is another group, this is a different treatment entirely. One plant also subjected to that treatment, another subjected to that treatment, like that. And this is C, and the same thing applies. Now you want to know if there's a difference in the level of treatments. In the treatment, this treatment A of 10 mils, is there a significant difference between this and this one of 30 mils per day? Is there a significant difference? That's what we are trying to test. So that brings us to null. We have the null hypothesis. The null hypothesis states that there is no difference. There is no difference. That means treatment A is the same as treatment B and is the same as treatment C. There is no significant difference between the treatments. And the hypothesis, the alternative hypothesis, tells that there is a difference. So which one are we to accept? Are we to accept the null hypothesis, or we are to accept the alternative hypothesis? Then that's when we are now talking of ANOVA. Let's now use ANOVA to test whether we are to accept that there is no difference, that is the null, or whether we are to accept that there is a difference, that is the alternative. Now, so I believe I've done justice a little to the terms, to some of the terms. Okay, so this is the treatment. These are the treatments A, B, and C. These are the replications 1, 2, and 3. In ANOVA, in order to test if there's a significant difference, we need to know the differences between each groups. That is, if there's a difference between A, B, and C. And we also need to know the differences within a group itself. In this group, any difference within, that is in group A, is there any difference within group B? Is there any difference within, and the likes? So differences between, differences within, that's what we are trying to get. And in order to test for that, we need to know some things. Firstly, we need to know the sum of square treatments. We also need to know the sum of square total, and we then need to know the sum of square error. Now these things, we need them in order to finally compute whether we are to accept the null or to reject the null. So sum of square treatment first. What is the sum of square treatment? Sum of square treatment is just simply the summation of the treatment squared divided by replication minus grand total all over total sum, the number of all the elements. That's the sum of square treatment. Now sum of square total equals to summation of each of the variables, each and every of the variables in the both along the row and column. Sum the square of all the variables, then still with this. And sum of square error will then be sum of square total minus sum of square treatment. So these things, we need to know them first. So first and foremost, what is the summation of the treatment? Because we need to first test the sum of square treatment. We need to first compute the sum of square treatment. Remember, we said sum of square treatment is summation of each of the treatments. Summation of each of the squared of each of the treatment divided by the replications minus the grand total minus the grand total divided by the number of the elements there. Okay, now coming to this, the treatment, each of the treatments, let's try to find the sum. This is 5 plus 7 plus this is 9, and this is 7, 11, and this is 18. This is 6 plus 6, and that's 5 plus 5, sorry, and that is 10. Sorry, this is 17, Okay, now that we've done this, we've known the treatments, the summation of the treatments. Now let's try to find the sum of square treatments. Sum of square treatment, that's 9 square plus 17 square plus 10 square all over. How many replications do we have there? We have 4 replications, so divided by 4 minus the grand total. The grand total will be the summation of everything if you had all the elements there, and if it's same as adding everything here, and that should be 36. So 36, the grand total is 36 squared all over the total number of elements there. You have 12 of them. Roll, by the time you had all the elements in the rows and the columns, you have 12 of them. So in the end we have 470 divided by 4 minus 7, this is divided by 12, and at the end of the day the answer should be 9.5. Okay, now we've known the sum of square treatment. Now let's get the sum of square total. The sum of square total. Remember I said sum of square total is you sum along the row and column. That's the meaning of this I and J. Along the row and column you sum all the variables, the square of all the variables, then still with the grand total divided by n. Okay, so now I wouldn't write all the variables out because I have 12 of them. So the point is, this one you square it, this one also you plus this one also you square it, plus this one also you square it, then you continue that way for everything. That's the meaning of that other part. So 2 square, so 2 squared plus 2 squared plus 3 squared, and it goes on like that, minus 36 squared all over 12. So in the end, if we calculate that, at the end of the day we should have 20, as everything all together should be 20. Now we've gotten the sum of square treatment, we've gotten the sum of square total. Remember, sum of square treatment is actually the difference between each of the variables. Now let's get the difference within, and that's sum of square error. That will be sum of square total minus sum of square treatment. Now sum of square total is 20, sum of square treatment is 9.5, so at the end of the day it should be 11.5. that is the sum of square error. Okay, now we've used the table, we've gotten the sum of square treatment, we've gotten the sum of square total, and then we've gotten the sum of square error. Now that brings us to the ANOVA table. Now this is not actually what we are trying to aim at this is not actually what you are trying to know for your exam. What you are trying to know for your exam is what we're about to start now. Okay, now the ANOVA table, this is the ANOVA table. So here are the variables or the source of errors. Number 1, the error can come from the treatment, and it can be the error, and then we have the total. Now the next one is the degree of freedom. That's how much freedom you have for each of the variables, each of the source of error. Now degree of freedom for treatment, I'm going to write the formula first. That's treatment minus 1. Degree of freedom for error is treatment into brackets replication minus 1, and the degree of freedom for total is treatment times replication minus 1. The next thing to know is the sum of squares. Then here will be the sum of square treatment, which we got earlier. Here will be the sum of square error, the other one, and this will be the sum of square total. The next one we need to know is the mean square. Now the mean square will then be the sum of square treatment divided by the degree of freedom for treatment, and the mean square error is sum of square error divided by the degree of freedom for error. Then after, we can now find the F ratio for the calculated, because we need to know the value of the calculated and the value of this for the calculated value of analysis of variance for calculated. So that's F calculated, and the F calculated will simply, if let's assume this one is C and this one is D, so it becomes C divided by D. That means the mean square treatment minus mean square error. So whatsoever we have here, we then use to judge whether to accept the null hypothesis or to reject. We then use to judge. So now quickly solving what we need, what we already have, trying to bring it together. So treatment error total, treatment, we have 3 treatments, remember. So degree of freedom for treatment, and this is where we all need to take note of, because this is how they set their questions. Now the treatment from the table, we have 3 treatments, so this place should be 2. Remember, treatment minus 1, that's the degree of freedom for treatment. Now for error, we have treatment to be 3 and we have replications to be 4. So firstly, replications minus 1, that's 3 minus 1, 4 minus 1, that's 3, and 3 times the treatment 3, that will be what, 9. So the sum of square total will be treatment times replication, that's 3 times 4, and that's 12 minus 1, 11. And if you notice, you will see that 2 plus 9 gives 11, 11 minus 9 gives 2, and like that. You should be able to do the calculations. And for the sum of square treatment that we got the other time, we got 9.5 error. So remember, this one is 10.5, then this is 20. So the mean square would then be the sum of squares divided by the free degree of freedom. So this place should be 4.75, and this one will be 1.15. Sorry, this place will be 1.17. Then we can now calculate the F calculated. The F calculated will then be the division of these two, and that's 4.06. Okay, so before we move on, let's now try to see how questions will be formed from things like this. The questions come this way. For example, in an analysis of variance, if the treatment is, sorry, I'm not going to write the question in full, I'm just going to write out the parameters, but you can follow what I say. If the treatment is free and the replication is 4, what is the degree of freedom for error? That's how you see questions in your exam. What's the degree of freedom for error? Remember, degree of freedom for error is what? Treatment into bracket replications minus 1. So that's what you just simply do. 3 into bracket 4 minus 1, and that's 3 times 3, 9. As simple as that. Okay, you might also get questions like, if the sum of square error is 11 and sum of square total is 15.1, what is the sum of square treatment? So remember that sum of square treatment, sum of square total equals to sum of square error plus sum of square treatment. So sum of square treatment should then be what? Sum of square total minus sum of square error. So that will be 15.1 minus 11, and that should be what? 4.1. That's how questions would come in your exam. Okay, you also get questions like, if the mean square treatment is 2, the mean square treatment is 2, replication is 2 and treatment is 3. Find okay, and also let's say the sum of square, and the sum of square total is, take for example 10, or let's just say 20. Sum of square total is, take for example 20. Find the sum of square error. Now you remember that sum of square error, sum of square total is sum of square error plus sum of square treatment. So that means we need sum of square treatment, but the question only gave us mean square treatment. And how do we get sum of square treatment for mean square treatment? Remember that from the table, sum of square mean square treatment equals to sum of square treatment divided by degree of freedom for treatment, which is what? Treatment minus 1. Okay, so we can then say sum of square treatment will be what? Mean square treatment times degree of freedom for treatment. And mean square treatment here is 2. Degree of freedom for treatment is also 2. If you use the treatment here, it's also 2. So times 2, which is what? 4. So since we know that the sum of square treatment is 4, we can then say the sum of square error will then be what? 20 minus 4, and that's what? 16. Okay, and that's just how questions go in ANOVA. That's how they set questions in ANOVA. You do not really, though you can always have the knowledge of how to get the sum of square treatments and the likes, but then questions are formulated around this table. Now finally, in order to know whether to accept or to reject, because you won't be allowed to go in with ANOVA table, no, you won't be an F table, you won't be able to you won't be allowed to go in with it. Remember we said we need to know the F calculated, and the F calculated is what we already have here. F calculated is 4.06, but we also need to know the F tabulated, the one on the table, ANOVA table. And how do you check F table? You just simply check it under the degree of freedom for treatment. You check the F table under 2 and 9 with the level of significance, and most usually the level of significance is always 5%. So once you check this on the ANOVA table, whatsoever you get, I'm checking this on ANOVA table, that's the value is 4.26. now here is now to take the decision. Taking the decision is now what is left here, and the decision is that if F calculated is greater than F tabulated, reject H0. That's the decision. If F calculated is greater than F tabulated, then you reject the H0. Now let's see if what we have here. F calculated is 0.4.0306 rather, and the F calculated is F tabulated is 4.26. Now you see that F calculated is less than F, so then we do what? The decision is to accept H0. So how would questions come in this form? You will be given the value of the F calculated. You will surely be F tabulated, sorry, you'll be given. So you might be given, probably the question might now go on and say if the mean square treatment is a value, let's take 16, and the mean square error is 4, and the F tabulated is 4.1. In this hypothesis, are we to reject or to accept? So firstly, you need to know the F calculated, and remember they've already solved it up to this point for you. So an F calculated is mean square treatment divided by mean square error, which is 4. And since the F calculated is 4 4 is less than 4.1, so you do what? You accept the null hypothesis that there is no significant difference in the level of treatment. So from what we have just done, from that table that we've done, it tells us that ANOVA, the analysis of variance, is telling us here that we are accepting that there is no significant difference. So from what we have up here, exactly this is it. From what we have here, the table, what we saw is down the other time, since our F calculated is less than F tabulated, then we have to accept. Because this thing is, if F is greater, F calculated is greater than tabulated, we should reject, but this one is less, so we are accepting that there is no difference between the level of treatment from what we have here. So that's just all about one-way ANOVA. In the next video, we're going to be treating the two-way ANOVA. There isn't much of difference actually, it's just one thing that differentiates them. So bye.